Hello everyone and welcome to algotrading.pro. In this video we are going to try to use a locally estimated scatterplot smoothing method, aka LOESS, in order to trade with Zorro Trader. So LOESS is not a technical indicator, but you can sort of use it as one. And it is not implemented in Zorro Trader. So I thought it would be a nice programming exercise and, a bit of trading experimentation to use, Zorro Trader as your trading platform and call R into service in order to implement this LOESS smoothing filter. So what in the world is this LOESS smoother or filter? Well, actually, look, it's very simple. So this is a stock chart, right? So every dot here, so the data set at hand, every dot is a closing price, right? So we have the stock price, we have the date. And here we are fitting a line to this stock price chart. And of course, this line captures the trend fairly well. This stock is going up, but then, is this very useful in trading? Well, not really, because, stocks do crazy things all the time. So, this blue line here is not the most useful thing in order to trade the stocks. So this is a simple linear regression fit. And it's probably the simplest smoothing mechanism one can think about, but it clearly over smooths the data. And then, of course, you're familiar with simple moving averages and exponential moving averages. Every trader out there has some understanding of these. And then, of course, in Zorro Trader, we have a better version of these moving averages, which is a low-pass filter, actually more than one. But this video is not about that. If we look here on the right side, you've probably seen something like this before. If you fit a moving average or a low-pass filter to the data, you get something like this. But this is not that. So this blue line here, which as you can see, it's very smooth. This blue line is not a moving average, and it's not a low-pass filter. It is a different smoothing mechanism, which is this LOESS procedure that I wanted to talk to you about today. And as you can see, you can make this as smooth as you want. And please notice that the problem of the lag is not as significant as in other with other smoothing techniques. Okay, so what in the world is this LOESS method? Well, it's actually a very old smoothing filter. The R package is kind of new, the one that I'm going to use here, but for those of you who are mathematically inclined, Savitsky and Golai have developed a filter in 1964, a filter that is mathematically equivalent. It's not identical, it's not the same, but mathematically it's equivalent to the LOESS methodology. And it was known and used at the time, but then later, much later, William Cleveland, which is a noted personality in the field of filters and signal processing, stuff like that, he kind of rediscovered it in 1981 and sort of made it popular. And please note that at the time, what he was proposing was something with the letter W in here. So I really don't know what the difference in pronunciation is between low low ESS, or LOESS and LOESS. But anyway, this was the older version, the grandfather of the modern LOESS package. It was developed in 1981, and then he improved it in 1988. LOESS, this version only did linear regression, and this guy here, the new version, does polynomial regression as well. The R package that we're using, I think, was developed in 1992. So the main difference between these two is that the first version was only doing local linear regression, while the last version does both linear and polynomial local regression as well. So what do I mean by local regression, right? So we all know what linear regression is, right? You fit the line to a set of data, right? But why do we say local regression here, right? Well, that is because the way in which we achieve this smoothed curve is by a procedure that is very different than moving averages, for example. So look at this picture here. So we have our data set, the blue dots, right? Let's say closing prices, whatever, right? And then what we do is we select a window. This is like with moving averages, right? We select a window, and these are the red points. And then for every single point in this window, starting with the first one and ending with the last one, we repeat this procedure. Right now, we are calculating the value of the smoothed curve for this point here, right? This dotted dashed line, blue line shows it. So basically, how do we get the value of this smoothed curve for this point here? Well, first we need a window size, and we have a window size here. The red dots are whatever the number is here, and then we fit a linear regression line here, right? But this is not the least squares linear regression, the classical one. It's a weighted linear regression model. What that means is that this point here, this is the focal point for this window right now. The points that are closest to this point, like this guy here and this guy here, these 2 points get more weight in the calculation of this line than this guy or this guy and these guys here, right? And the green curve here shows those weights, right? So this is a function that's being used, this green line, to calculate how much weight each one of these points gets. And you can see here, right, that the weights, on this plateau here. So this is not a bell curve. This is not a Gaussian curve here. So you can see that up here, the close neighbors of our focal point here, the close neighbors get weights that are 1, right? And then the further away these the red points are from our focal point, right? The further away, the lower the weights. And outside of our window here, outside of this window made out of red points, outside of this window, all the other points get weights of 0. Okay, you can see this in the green graph here. So this point has no effect on the slope of this line. This point has no effect on the slope of this line. This point does have a little effect on that slope. This point has a little effect on that slope. These points here have the most effect on this slope. So this is a local linear regression, a weighted linear regression, not a simple linear regression. This is how we calculate, these points here. So for every single point in this data set, we can do this over and over again, this procedure, and we will get so the next step, this guy here becomes the focal point, and everything moves to the right by 1, and so on and so forth, as you can clearly see in this animation here, right? And so this locally fitted line, of course, changes slope according to the window and the weights, and at the end we get this nicely fitted line. Now, actually, it is a bit more complicated than this, because we have horizontal weights here, and this means that the further away this point is from the focal point, the less weight it gets, right? But the real procedure also have vertical weights, meaning that the further away a point is from this focal point, on the vertical axis, meaning the higher the probability that point is an outlier, the less weight that point receives. So it's a local regression, local linear regression procedure, but it is weighted both horizontally, like here, and vertically, something like this, right? So if a point is very far away and it's most likely to be an outlier, that point is going to exert very little influence on the slope on this line, right? Which makes this method pretty robust to outliers, okay? So this second weighting mechanism is not represented here for simplicity, but I'm sure you understand. You just translate this curve, you just rotate it by 90 degrees, right? And then you get the vertical weighting as well. The mechanism is the same, right? So this is how we obtain this smoothed curve here, and this is the LOESS, the locally weighted linear regression procedure. But think about it. Right now we are fitting a line to these points. Can we fit a curve to those points? Absolutely. Absolutely. So instead of fitting here a straight line, right, we could fit a polynomial of a degree 3 or 5 or 7, which would give us a curve here instead of a straight line. It's the same thing. I mean, the point on that curve fitted on these points, the red ones, corresponding to this point here, that point on that curve would be the point on the LOESS smoothed curve, if you will. So, here we have basically a visual example of this procedure, and the modern version can use both linear lines here, but it can also use polynomials, meaning curves. And actually, there is a parameter of the R function that we're going to use that allows us to control for that. Okay, I hope that this makes sense. And right now, I am going to show you the R function that we will use. It is in the stats package. I think it's installed by default with my R installation. If that's not the case with your installation, then of course make sure you have it. But anyway, the function is rather simple. So it takes so the function is called LOESS, and it takes input data, and it has multiple parameters, but the ones that are of interest for us are the span, right? The span, which means the parameter that controls the degree of smoothing, okay? And what exactly we mean by that? Well, it is actually, I will show you the number, it's a proportion of the data points. So remember the red dots in our picture versus the blue dots. So alpha controls the ratio between those points. So if we use, let's say, half of our points to fit a regression line or curve, then alpha would be 0.5, right? So this basically controls the smoothness of the curve, right? And then we have another parameter here that is important. It's the degree of the polynomials that you can use. So if you use a polynomial of degree 1, then you fit a straight line to the points. And if you use a polynomial of degree 2, then you fit a parabola, right? A curve to those points, right? And degree 0 is also allowed, but here in the notes, they're telling us that it's search for it here, but they're telling us it's not really a good idea to use it. But anyway, so and here is the book if you are interested, by Cleveland and co-authors, local regression models. Okay, so this is the function that we will use, and let me start by showing you a toy example, right? So I will fire up R. Actually, I think I did already. Sorry about that. So I don't want you to watch me code here. So I already typed this for you. So basically the data, so the model, the data that the model requires is a data frame, right? And on the horizontal axis, it's just a sequence of numbers, right? For 1 to 14, that's going to be on the x-axis. And on the y-axis, let's say this is the dependent variable, right? We have the values. Let's say these are closing prices, right? This is a toy example. I'm just making this up. But let's say these are days, the first day of our simulation, the last day of our simulation, 14 days, right? And then here are the closing stock prices for each one of those days. Okay, so let's plot this. Let's see how it looks like. Okay, so the market goes up, and then the market comes down, and then the market goes up again, right? And okay, how do I, so if I fit up, I can fit a straight line here, right? We know that's not a good idea. We can fit moving averages, exponential moving averages, low pass filters, whatever. But in this video, we choose to fit here a LOESS model, right? And we have to provide the data frame where the data lives, right? And we have to tell the function, the LOESS function, which one is the dependent variable, right? And which one is the independent variable, right? So here we have x and y. And then we have to tell the function about the span, how much of the data will be used, what percentage of the data will be used to fit the curve to every single point here, right? So the smaller the value here, right, the jaggier, the noisier the curve will be. Probably not very visible in this small example, but anyway, so the larger this number is, the more data will be used to fit the model, so the curve will be smoother. And then the degree, right? The degree equals 1. This means we're fitting a straight line and not a polynomial. So if we do this means polynomial. So if we put here degree equals 1, this is basically LOESS, with, well, whatever the pronunciation is with the W here. Well, we will play with these a little bit, so you will see the difference. But anyway, let's fit the model. Now we have the LOESS model, and let's take a look at it. Well, let's take a look at the model. So what do we see? That the object is, this object here has multiple components. What we're interested in is this fitted component. We don't care at this point about the residuals and whatever, So basically this here is the fitted model, right? And this is what I'm using here into the plotting procedure, right? So I'm taking out the LOESS model, the component called fitted, right? So you can see it here, right? So once we run this, right, we are going to get a fitted curve, right? So these are the closing prices, right? For our 14 days simulation, and the red line is a fitted curve that, well, it's a curve, but it was obtained by fitting straight lines according to the procedure you've seen before to these points. Now remember, if we want to fit polynomials instead of straight lines, then all we have to do is to change this number here. So the degree of the polynomial is now 2. Before that it was 1, right? It was fitting straight lines. Now it's fitting curves. And if I run this, as you can see now, because I'm fitting curves, the line is closer to the points. The line is closer to the points. The root mean squared error is probably, well, not probably, but for sure, smaller when we fit curves to these points. So now before we were fitting lines, right, like this, and now if we change this degree to 2, now we are fitting curves instead of lines. Okay, I hope this makes sense. And now let's see the effect of this span parameter. So if I make it 4, right, instead of 5, I mean .4, not 4, the data fits better. But if this were a bigger data set, you would get a very jaggy LOESS curve here, right? If we choose to use more of the data for that window, for that smoothing window, right, we will get a much smoother curve, right? So this parameter here basically controls how smooth the curve is, and this other, the span, right, and this other parameter here, degree, controls if we're fitting curves, meaning polynomials like now, or fitting straight lines, like I'm gonna do now, right? So as you can see, depending on what you want from this smoothing procedure, you know, you can choose various, you know, parameters, these two plus many others, but I guess you get the grand idea. Now, why did I bother with this R code here? Well, that is because this R code is what we will use in Zorro Trader in order to trade this. So what I want to do, this is of course a toy example, but it's gonna work the same nonetheless, right? So what I want to do is I want to send R from Zorro Trader, you know, these points, right? I want to send R from Zorro Trader, these closing prices, the last 14 in this case. We're gonna send it more, but let's say this is the case, right? So we want to send from Zorro Trader to R these 14 values, and then we want to get from R not this whole curve, because this whole curve is something that happened in the past, right? It happened already. I can't trade this point here because it's gone, right? It was 6 days, well, whatever number of days ago, right? But this guy here is the value of this curve today, right? So I need some sort of a look back period. So I'm gonna send to from Zorro Trader to R this data set, right? With this sort of a look back period, if you will. And then I'm gonna get back from R this value here, this value, the last value here, right? So I'm going to show you how to code this in Zorro Trader based on what we've seen here, right? So what matters most is probably this line here, right? That is the line that generates the model, but there is, of course, more to this coding exercise than just what we're doing in R. However, make a habit when you want to use Zorro Trader and R together, make a habit of starting in R, right, with something like this, and then go to Zorro Trader and use what you've accomplished here in order to trade with Zorro. Okay, so just to make sure that there is clarity here, so basically we're taking a set of points and we are going to use the past here, right, to predict the current value of the fitted model of the lowest curve. And we are going to return that last value from R to Zorro Trader. We don't care about these previous values because those are the past. We cannot trade these. I would have gone short here or go long here, but this is gone. This has happened already, right? All I can do is look at this value and you know, keep doing this again and again and again. And generate the curve that is in the present, right? The curve that I could trade, right? Okay, so let's fire up Zorro Trader here, and I already typed the code here for you. So let's go through this code kind of line by line, right? So the first thing that you need to do, really need to do this, is because not in all the examples in the Zorro Trader manual do you see this, but every single time when you want to use R, you have to include this, you have to have this directive here at the right at the beginning of your code, you know, include this library, this R library, which the R header, because without this, your code will not work. This is a library that's necessary so that Zorro Trader can talk to R. And then, you know, we're starting an R session here, and we could have probably done this like this, but I don't want that. I'm not starting an R script here. The commands will be given straight from R, but you could have used the script here. And I'm adding this parameter 2 here because I want a verbose output. So I want Zorro Trader to print anything that R is telling us. And then if R didn't start, right, then print an error, could not start our session, right? So if you didn't configure your R configuration in Zorro.ini correctly, or Zorro fix ini, then this isn't gonna work. But remember, you have the R test script that you can always, you know, use this R test script to check if R works correctly for you. Anyway, so now we have a correct connection between R and Zorro Trader and R, and you know plot now, and you know bar period by now. We're trading daily data, and I'm programmatically selecting my asset as Apple. Please make sure you have an entry for this asset in your asset fix file, otherwise this is not going to work correctly. And then, you know, there are 2 parameters that we need to concern ourselves with. One of them is characteristic to Zorro Trader, sort of, if you will, the other one to R, right? So if you remember, the span parameter is basically what we need to tell Zorro here, right? And then we also need a size for this price series that we are sending to R, right? So the size in this toy example here was what? Well, it was 14, right? The size of these price series is 14 values, right? Now 14 values is not, it's not good. We need more than that. And here arbitrarily I chose 470 values. So basically, the length of the price series that we will use in order to calculate the LOESS smoothed curve, it's going to be the size of that array of that series is going to be 470 closing prices. And the degree of smoothing that I chose here is 10%, right? So the span is 0.1. So we will use 10% of the data as our sets of red dots versus the blue dots. Okay, now here Zorro Trader knows how to calculate the look back automatically, right? So here we can't go back more than 400. I mean, 470 values is what we need. So Zorro knows how to calculate the look back, and while we are in the look back period, we're doing nothing, right? So we're just returning here. But here is where the magic happens. So first we are sending to R from Zorro Trader using the R set command, right? We are sending the price data and we are sending the span, right? The smoothing parameter, right? And here is where stuff gets tricky. So basically, well, this is simple, right? So we are, the command rset defines a variable in R called span, and it sets that value, it initializes that value to the Zorro Trader value called span, which is 0.1 here, okay? Of course, you can change this, and you don't need to change the code. Now, what in the world is this thing here? All right, so why here this variable is this guy here, okay? So that is our dependent variable. That is our dependent variable, is a series of 470 closing prices, right? And the parameter size is needed here because this is C, and C does not measure lengths of arrays and stuff like that by itself. You always have to specify, right? Now, if you look into the Zorro manual, sometimes these parameter is omitted, but that doesn't mean it's not there. If you don't specify the sizes here, then Zorro will use the look back period that is specified or calculated. And it is not always the case that you want that. I mean, for whatever reason, your look back period, not here now, but in other scripts, you want a look back of 500, but you want the size of whatever you're passing to be 20, right? So then you have to specify the size here. But why twice? Well, because in Zorro Trader we have zero indexed arrays. In Zorro Trader, price close of 0 index 0 is the last price, while in R the value, the index 0 is the first one. Okay, so R and Zorro work in an exactly opposite fashion when it comes to array indexing, right? Of course, this in R is called a vector, but it doesn't matter. So the first value in R is this value here. Well, in Zorro, this is the last value. Okay, so because that is the case, we have to use here this reverse function, right? And this reverse function takes as argument this array, which is a series of closing prices. This is a pointer, actually. It's a function that returns a pointer. It's like a series of closing prices, but we are just using a simpler thing than creating a series of price close and so on and so forth. And then we have to tell the reverse function what the size is so we can reverse it correctly. And then when we pass this array of this array of prices, this series of prices, which is y here, right? When we pass that to R, again we have to specify the size. Okay, so we need the size first when we reverse the price series, and then we need it again when we pass this array of numbers to R from Zorro Trader. Woo! I hope this makes sense. So this is probably the most difficult line of code here that you have to understand, because this is basically, this makes use of Zorro Trader features as well as R features. So this is the variable name in R, this is the variable name in R, and this is the variable value from Zorro Trader, right? It just so happens I call them the same thing, but you know, and here is, you know, an array instead of a float, a number, right? Here is an array, a series. But this is the data that we're sending from Zorro Trader to R. Historical prices and a span, right? And then, so the command rset creates and initializes these variables in R. And then we have our beloved rx command, which means this is r set, right? Set these variables. Here is r execute, right? R execute. So what does R need to execute? Well, it needs a independent variable, right? The x variable, this guy here, right? And this is just a sequence, guys. It's just a sequence of numbers, right? And there is a more elegant way to do it than I did it here, and that is, you know, we are just creating a vector starting at 1 and making it as long as the length of the price series. So here it's going to be 470, right? And call it x. All right, so this x value here together with that y value, I mean arrays, both of them here, they will then become the data frame that R needs, right here, okay, in order to make things work. So now we told R that we want the prices to be stored in the y variable. You know, we created an x variable that's just an internal counter that we need, and then we have, you know, this line here, the LOESS model, right? So that is another R execute command, right? And we're defining a variable in R called LOESS model, and we use the LOESS function. The two variables that we have defined, right? Data is equals to the data frame. We just did that here. And then we have span equals span, meaning this value here, okay? Does this make sense? I hope it does, right? So then we can define another variable here called LOESS. I'm sorry for my lack of imagination when it comes to variable names, but this is going to be the fitted component of the LOESS model, right? Pretty much this guy here, right? But we're not representing it graphically now. We are just defining this variable. But now here is the tricky part. Well, not really tricky, but if you remember this LOESS model $fitted, that is a vector, an array, right? It has all these values, right? All these values in it. I don't need all these values. I only need the last one. I only need the last one, right? So this is something that's not in here, but what I'm doing here is I'm executing another R command, and I'm defining an R variable called LOESS last value, and then I'm taking the tail, right, of this LOESS underscore model $fitted, right? That's a vector, and I'm taking the last value here. So basically what this R function does, it takes the LOESS model and it generates a value that is the last value in this array, right? So it's this guy here, basically, not that guy, that's the data set, but this guy here. I only want this value because this is the value of today, right? I don't care about the past. I can't trade this, it's gone, right? These days are in the past, they're gone, but I need this value here. Why? Because I want to construct here in Zorro a series, right? A series like a simple moving averages, average, or a low pass filter, or whatever. I want a series that I can trade, right? Or plot. And I'm defining here in Zorro Trader this vars variable, which is an array, a series. I use the function series of Zorro Trader, and then I am using the RD function of Zorro Trader that recovers from R, right, this variable. So RD is R decimal, right? So this is a value. This is not an integer, right? It's a value that has a decimal point. So I think that's what this D stands for. But I'm taking this value here. So this command was executed, right? And now this variable is defined and initialized, and then I'm using it here. I'm retrieving it in Zorro Trader from R here using this command. So basically, every single time when this run function is run, meaning at each bar, right, I am sending to R from Zorro Trader 470 values, closing prices from the past, and I'm getting back one value, which is the closing of today, if you will, right? That's pretty much it. And I will not see this for the look back period for the first 470 values, because I need those to calculate this one value here. But then at every single daily bar, I will get a new value that goes into this LOESS series array. Okay, so I'm hoping to obtain that smooth curve that is not a moving average, and it's not a low-pass filter, right? It's a LOESS curve. And what is my trading logic here? Well, if the curve is smooth enough, right, and if it doesn't have too much lag, then the very simple strategy of finding peaks and valleys, right, into this curve, you know, if I have a valley, meaning the market goes down and then it comes back up, you know, I'm entering a long position. If I have a peak, meaning the market went up and now it's coming down, you know, I'm going to enter a short position. And then I'm going to plot this LOESS curve, right? I'm going to plot this red. Well, it's going to be orange, but you get my point. Again, I'm not going to see this for the first 470 points because I need those to calculate the first point in my visible and tradable, if you will, LOESS curve. But you know, you get my point. Okay, so I will you know, I did not touch other parameters here than the span, right? Remember that you can add here and play with the degree as well. If you want so by default, what we're doing here, right, by default, the degree here is 2 by default. So we're fitting a curve. We're not fitting a straight line. If you want to fit a straight line when generating the LOESS curve, then you have to do this, right? I'm not doing it, but you know, feel free to play with this at home and see what happens, right? So right now we're pretty much using only this span parameter and, you know, the historical data that we want. In this case here is 14 days, right? In our case here in Zorro is 470, and the span is 0.1. So let's see what we get, right? So let's see what we get. So this isn't optimization, guys. It's nothing. We're just, so please don't trade this at home, okay? This isn't investment advice or anything. This is just a programming exercise in which we take, you know, a number of historical values from Zorro, we pass them to R, we get the value of this graph here today, and then we build a series with that. And then we are trying to see if, you know, in a back test, if this would have been profitable in some way, shape, or form or not, right? Okay, so let me just run this, and something went wrong here. Not sure what, but okay, so basically this is pretty much what we expected, right? So we have a you know, an annual return that's decent. It's doing better than the 9% that the S&P 500 usually does. The Sharpe ratio is not nice. It's 0.63, but you know, maybe we can improve this. This is just the first shot at the problem. So what I wanted you to see here is, you know, this orange line, the LOESS curve. And I wanted to point out to you that if we would have had a moving average of, you know, size 407, the formation period of 470, you can imagine that would have been a very slow moving average, very slow, right? But look at this curve. Look at this curve. Does it lag? Yes, a little bit. It lags a little bit, okay? But overall, it follows the peaks and troughs of the price curve very nicely, very nicely, okay? So is this a very profitable strategy? No, but think about it. First, this is a trend following strategy, right? So it's gonna work great when a trend exists. And look at these beautiful trades here, right? Short trade, long trade, right? Short trade, long trade, you know, good long, good short, etc. Look at this sequence of good trades, right? So when a trend exists and it's strong enough, as you can see, there is almost no lag, and trading the peaks and the valleys, you know, works pretty nicely. Then, of course, because it is a trend following strategy, it fails miserably when the market is mean reverting, like here, right? We knew that already, right? So when the market is mean reverting, I mean, look at this. The market starts here and then it ends at the same place, right? So when the market is mean reverting, of course, it fails miserably. But that is not the point. The point is, you know, we are getting, you know, a LOESS curve here. And even in the most rudimentary form of trading, you know, peaks, valleys, we're getting a decent return, right? So what I wanted you to notice was that the entry signal is almost never wrong. The entry signal is almost never wrong. So look at this. We entered the signal on the next bar, on the next candle, because this was a valley, right? The market did go up, okay? So the signal wasn't wrong. The entry signal wasn't wrong. But the exit signal, I mean, we have no exit signal, right? So the exit signal is basically a peak when you know, the market starts going down, right? And this signal isn't wrong either. I mean, the market did go down by a lot. So, you know, we may need to work on the exit signal here. But as an entry signal, you know, both the valleys, the troughs, and the peaks, right? They prove to be fairly good entry signals, right? Look at this guy here. Now, one thing that I want you to notice is that we enter trades sometimes when there is not really a peak or a trough, or it's a very small one. I mean, look at these things here, right? So we also probably need a filter. I mean, some of these peaks, if you will, are not really peaks. They are too small to be peaks, right? This is a good peak. This is a good valley, clearly. But you know, if you examine this curve very closely, you'll find examples of what I wanted to demonstrate here. Peaks that are too small. But this is a completely different conversation. How do you make this strategy better? And again, we're not optimizing. We're not, you know, doing anything. I just wanted to show you, you know, how you can, you know, use a mathematical modeling, you know, a mathematical filter called LOESS. You can use it as a smoothing filter. Zorro Trader does not have it, but R does. So what I wanted to show you was, how do you call R into service from Zorro? How do you pass data from Zorro to R and back? And then how do you use that data in order to build a sort of a tradable strategy? So, or at least a decent backtest. Now, you know, since we spoke about degree, one thing you can do here is play with that degree variable, right? So right now it's 2. right? So right now it's a polynomial of degree 2. But if we wanted to fit not a curve but a line, you know, let's see what we get. Who knows? Maybe we can improve this. We wrecked it. Now it doesn't work. So, all right. I'm sure you get my point. Remember that so the function has a lot of variables. This function LOESS. You can try playing with them if you will. But overall, this is the grand idea. You know, I hope this makes sense. Come visit us at algotrading.pro and subscribe and like our videos, and subscribe to our channel if you didn't already. And until the next time, happy trading.